we have learnt about electromagnetic field carrying energy. I just want to tell you that S, which we wrote as 1 over mu 0, it is easy to show that the magnitude of S is also equal to the energy content, energy density times C. Okay, I will leave this as an exercise for you. So, it is like, if there is a water in some container or some liquid of density rho, and if it is flowing with speed v, then the flow of the water moving per unit time is the density times the velocity. In the same manner, energy flow per unit time per unit area is u times c. I am saying this now because I will use it in the momentum equation that I am going to use now, introduce now. The electromagnetic field also carries momentum. EM field also carries momentum, and this can also be derived exactly in the same manner as we derived the Poynting vector, except that the derivation is a little more complicated and slightly beyond the level of this course. So, I will just state in dimensional way that this S, which is nothing but energy flow per unit area per unit time, which has the dimensions of m v square over L square times time, is related to the content of momentum or momentum density as follows. Momentum density, which is going to be m v over L cubed, that is the dimension. So, this is related to, this is the dimension of this, the S vector as S over c square, where c is the speed of light. What it means is, if there is in some region of space there is E field and there is B field, then in this region there is momentum content in this field. So, momentum density per unit volume, momentum is going to be S over c square equal to 1 over c square times 1 over mu 0 E cross B. Since 1 over c square is mu 0 epsilon 0, this can also be written as momentum density, can also be written as epsilon 0 E cross B. So, what it means is, if I take a small volume here in this region where the E and B field exist, the momentum content in this volume is going to be per unit volume epsilon naught E cross B. This is momentum density. Obviously, there is going to be momentum flow also, which is nothing but c times the momentum density, as I argued for the energy flow earlier. And this is going to be nothing but 1 over c times S, which is 1 over c times 1 over mu 0 E cross B. What I am concerned about right now is the momentum density, that electromagnetic field carries momentum, and I am going to now demonstrate this formula through an example. So, let us solve that example. Example I take is, suppose I have two sheets of charge. The upper one carrying sigma per unit area and the lower one carrying minus sigma per unit area, so that there is an electric field that exists between these two. The electric field is going to be sigma over epsilon 0 magnitude. Suppose now they also carry a surface current K going to the right side in the upper plate and to the left in the lower plate. Then by applying Ampere's law, you can easily figure out that B outside will be 0 and B inside is going to be, this is the direction. So, it is going to be going into this screen and its magnitude is going to be k mu 0. Therefore, S vector magnitude, which is 1 over mu 0 E cross B, is going to be equal to sigma k over epsilon 0, and momentum density is going to be 1 over c square sigma k upon epsilon 0, which is mu 0 sigma k. That is the momentum density or momentum content per unit volume in this region. How we are going to show that this is really the momentum density contained here is I am going to switch off k at the rate k dot. When we switch off this current k, this is going to reduce the magnetic field. If we reduce the magnetic field which is going into the board, let us go to the next slide. So, what we are doing is we have these two sheets which I am writing, just showing by line now, minus sigma. We have the electric field coming down, we have the surface current k going this way, k going this way, and we have the magnetic field going in all over. As k is brought down from Faraday's law, because B is now reducing, we are going to have electric field induced inside, and you can easily work it out. All right. Now, B is going in. I would like to have an electric field that produces B in the same direction because it wants to keep it the same. So, the electric field produced is going to be induced electric field is going to be like parallel to the plate, going to the right on the upper plate and going to the left on the lower plate. This comes from curl of E induced is equal to minus dB by dt. Using Stokes theorem, I can calculate the magnitude of the electric field. How would I do that? I will take a small loop of length L on the upper and the lower side, and the distance between the plates I will take to be d, then integral E dot dl equal to minus dB dt dot dA gives me that E times L times 2, because this contribution will come from the upper one and the lower one. I am traversing it like this. This I am going a little fast because you are used to it by now. 2 E L is equal to change in the flux, which is mu 0 k dot times the area, which is L times d. Let us again cancel L, and I get this induced electric field E to be equal to mu 0 k dot d over 2. This is the induced electric field. The direction of the electric field on the upper plate is like this. Let me make this plate again, and on the lower plate it is in the opposite direction, and its magnitude is mu 0 k dot d over 2. So, it will apply the force on this sigma and minus sigma. The force on the upper plate is going to be E times sigma per unit area. So, this is going to be mu 0 d over 2 k dot sigma per unit area. On the lower plate again, the force is going to be to the right, again mu 0 d over 2 k dot sigma. So, the net force on the whole system is going to be mu 0 d k dot sigma, and this should be equal to d by dt of the momentum of the plates of the system. where does this momentum come from? I am going to show that momentum comes from electromagnetic field, which is reducing, and therefore, the momentum of the electromagnetic field is reducing, and that goes into this mechanical momentum. We saw in the previous slide that the momentum density was mu 0 sigma k. So, momentum density is mu 0 sigma k. Net momentum content per unit area, this volume per unit area, which is going to be mu 0 sigma k, area is unity and the height is d, mu 0 sigma k d. So, what we have in these plates is that the momentum contained per unit area is mu 0 sigma k d, and as we switch off the k, then the momentum change per unit time, delta momentum per unit time comes out to be mu 0 sigma k dot d, that is the momentum that the plates gain. So, we can easily see as k goes down, the momentum of the field between the plates goes down, and that is transferred to the plates. So, what we have shown through that formula, that field carries momentum and it is transferred to plates. Finally, when I integrate over the entire time, the entire momentum mu 0 k sigma d will go into the plates momentum, because if I integrate mu 0 sigma k dot d over time, this comes out to be mu 0 sigma k d, which is indeed the momentum of the fields that has been transferred to the plates. Finally, when we are talking about the energy content, linear momentum content of the electromagnetic field, I will conclude this set of 3 lectures by showing that EM fields carry angular momentum also. That should not be surprising, because if there is momentum p, then angular momentum is defined as r cross p, and so with linear momentum, angular momentum is always associated. I will also demonstrate this through an example. So, if there are these electromagnetic fields E and B in certain region, we have seen that S is 1 over mu 0 E cross B. The momentum content per unit volume is equal to epsilon 0 E cross B, and therefore, angular momentum content per unit volume will be epsilon 0 r cross E cross B. Can this be true? Is this true? Again, we will show it through an example. The example I take is, we take a solenoid which is carrying surface charge sigma or charge lambda per unit length. This is surrounded by another solenoid which is also carrying charge lambda with a minus sign, minus lambda, and also carries a surface current, say going in on the right side and coming out on the left side. So, surface current like this. It is only the outer one that carries the surface current. Let the radius of the inner cylindrical shell be A, let the radius of the outer one be B. Then electric field E is 0 for S, I am using cylindrical coordinates, less than A. This is equal to lambda over 2 pi epsilon 0 S for S between A and B, and this is 0 again for S greater than B. Since there is a current in the outer shell, so the magnetic field B, is equal to, its magnitude is equal to mu 0 k for s less than b. And therefore, there is going to be momentum density which is going to be epsilon 0 E cross B between A and B. It will be non-zero only between A and B and 0 otherwise. Let us see the directions. E field is pointing away from the inner shell. B field is pointing up. So, E cross B is coming out here and going in here, because B is like this. So, E cross B is going in. So, what I have in this combination is that there is magnetic or electromagnetic momentum coming out on the right side of the shell and going in the left side of the shell. And since this is going around, it gives rise to an angular momentum. So, let us calculate that now. So, momentum density E cross B is going to be epsilon 0, E is lambda over 2 pi epsilon 0 s times B, which is mu 0 k. So, this comes out to be epsilon 0 cancels, lambda mu 0 k over 2 pi s. That is the momentum density. So, what I have is this solenoid and an outer solenoid, and in this region there is this momentum density which is coming out here and going in here, and its magnitude is, we have just calculated, is nothing but lambda mu 0 k over 2 pi s. How about the angular momentum density? About the common axis. Let me make this common axis, which is right in the middle, is going to be S, right, S times the momentum density. So, this is going to be lambda mu 0 k over 2 pi. Okay. How about the net angular momentum content? So, net at this point, the direction of the angular momentum density is pointing down, because this is S cross k is pointing down. On this side also, this is S cross k is pointing down, all right. So, this is pointing down, and net angular momentum therefore is going to be lambda mu 0 k over 2 pi. Then out here in this shell, and let us say net angular momentum per unit length is going to be 2 pi s ds times unit length, which is 1, and this is going to be from A to B. We cancel 2 pi and this comes out to be lambda mu 0 k b square minus a square over 2. That is the net angular momentum content between these two shells. So, if I make this again, per unit length in this region, per unit length, the angular momentum content is lambda mu 0 k over 2 b square minus a square. Again, we will use the same trick, we will reduce now k, reduce k. As you reduce k, the field B, which was like this, is going to start going down. Right. As the field goes down, as the field becomes smaller and smaller, so change in B will produce an electric field. Okay. And how would the electric field be? Electric field will be such that it generates field in the same direction, and therefore, the direction of the electric field is going to be like this, going in here and coming out on this side. By applying Stokes' theorem, I can calculate electric field at distance s from the center. 2 pi s E is going to be pi s square times B dot, which is going to be pi s square mu 0 k dot. That is the electric field formula. So, again if I cancel s, one s goes away, pi goes away, I get electric field is equal to mu 0 k dot over 2 s. That is the electric field produced. So, electric field at the E, at the inner cylinder surface is going to be mu 0 over 2 k dot A, and E at the outer cylindrical surface is going to be mu 0 over 2 k dot B. However, the inner surface has charge plus lambda, the outer surface has charge minus lambda, and therefore, the forces are going to be in different directions. The electric field is going in on the outer surface, right, and coming out on this side. So, because of the minus sign, it will give a force in the opposite direction. On the inner circle, it will be in the same direction as the E. Because of this electric field, the force on the outer shell is lambda per unit length is going to be equal to 2 pi B per unit length is per unit length times sigma, where sigma is the surface charge density times electric field, and this is nothing but lambda. So, this is lambda times E, which we have already seen is equal to mu 0 k dot B over 2, and therefore, torque on the outer shell is going to be lambda mu 0 over 2 k dot B square. In the similar manner, we can calculate torque on the inner shell, and it will be lambda mu 0 k dot over 2 A square with a minus sign, and therefore, the net torque on the system is going to be lambda mu 0 over 2 k dot B square minus A square. Net angular momentum of the system is going to be, when I integrate this, by the time k comes to 0 starting from some initial value of k, is going to be lambda mu 0 over 2 k B square minus A square. Where did this angular momentum come from? We have already shown that the electromagnetic field carries this angular momentum, which we calculated earlier. So, therefore, that angular momentum is now transferred to the cylinders, and so what we have shown is that electromagnetic field carries angular momentum, which by some mechanism can be transferred to the shells or the systems around it, and that is equal to the mechanical angular momentum gained by